Okay, we are almost there. Just a few more minutes, we'll be there. Let me put on my earphones. Okay, any questions before we get started today? Well, very good. No question. And let me share screen.
Professor Chu, I have a question, quick question.
Yes, yes, sure.
Are you going to have the office hours today?
Oh, today is going to be at 8 p.m. I'm going to make the office hours at night so that more people can participate. So Dr. Na will give the office hour tonight.
Okay, sounds good. Thank you.
Okay. Yeah, so today's topic, I'm going to talk about shielding. And then after talking about shielding, we will talk about image theory. And I will talk on different kinds of shielding and image theory. And then let me begin by just having a very simple picture of two conductors. Two conductors where you can assume that the conductors, one having a charge that is negative, the other one having a charge that is positive. And the conductivity does not have to be infinite. The conductivity can be finite. And in fact, you can argue by Duncan experiment or thought experiment that the field has to be zero inside this conductor, okay? E has to be zero here, and E has to be zero here. The argument is very simple. If E is not zero, then this is a conductor, J is equal to sigma E, and then here J will be equal to sigma E. Current will keep flowing if E is not zero, and current will keep flowing until the charges are in equilibrium such that the electric field is equal to zero inside before it stops flowing. Because of that, then it has to be that the potential is actually equal to constant, since E is equal to zero. In order for the current to stop flowing, it means that E is equal to minus grad phi. It means that phi is a constant. And also here, it means that phi, let me call it phi2. Phi2 is a constant. Phi1 is a constant. So if you have just two conductors, not necessarily being PEC, okay, not PEC. PEC stands for perfect electric conductor. The electric charges, the positive one and the negative ones, can shear each other out so that E equal to zero inside, just by a very simple argument. Can everybody follow this? That E has to be zero, conductivity does not have to be infinite. And then the electric field has to be zero, okay? What happens now if, say, if we bring a dipole near this conductive material, okay, this is time-varying dipole. And this time-varying dipole is time harmonic, so that at one moment it will be plus and negative like that, but another moment it might flip its sign and becomes like that, because this is a time harmonic dipole. So let's assume that the dipole is slowly varying. So when the dipole is positive on this side and negative on that side, it must have attracted negative charges to come to this side. But since this is a neutral body to begin with, so if the charges are attracted to be here, to be negative, there must be excess of positive charge on the other side. However, when this dipole flips over to the other polarity, then what happens is that the charges here would be positive, meaning that the other side would be negative, okay? In other words, when this dipole is time varying, the charges must be able to move back and forth between this conductive material in order to follow the change of the signs of the dipole here. And however, if the dipole becomes very, very slowly varying again, okay, the charges are able to move back and forth to keep track of the sign change of the dipole so that the electric field is essentially zero. You can take the limiting case that if this is a static dipole, the field would have been zero. Okay, if this is a time varying dipole, the field would not be zero, but keep going back and forth between the two polarity of this conductive material. So there will be some current flow inside this conductive material if this is a slowly varying dipole. And it's very hard to prove that. And you can prove that the field is not zero. So it's quite easy to prove that field has not been zero when you have a time varying dipole. And then field is not also equal to zero. But you can actually show by numerical simulations or solving some canonical problem or basic problem that the penetration depth of the field is on the order of skin depth. In other words, there will be a layer and very close to the surface where this penetration depth is the skin depth. Okay, skin depth penetration. So even though now the electromagnetic field can penetrate into the conductive material, the penetration depth is on the order of 2 over omega mu sigma, which is our formula for the skin depth, okay? And so if the conductivity is very high, the penetration depth is very, very shallow. And also if the frequency is very low, the penetration depth is rather deep, okay? So, and let me see. So this is the relaxation time. There's a relaxation time involved in order for this thing to move back and forth. And that relaxation time is actually proportional to square root of sigma over sigma. Okay, maybe I'm wrong about this. It should be just no square root sign, then the dimension is correct. So this is called the relaxation time. And it is the time it takes for the charges to relax back and forth between the two polarity. You can think of this as being very similar to the RC time constant. Say if I have a resistor, a capacitor, you can actually solve for the solution for this problem. You will have T over tau. Tau is RC. Okay. So if you think of this as being an RC time constant because it has the same unit, it has the conductivity in the denominator and then farads per meter in the numerator. This is resistor and this is farad. So these two things actually have the same time constant. Okay. So there's a time constant involved now in the relaxation of the charges as they move back and forth between the two ends, very similar to how the current would flow. Say if you have current flowing, and then it will have to be discharged on the next cycle. Okay, as the charge is charging the capacitor and getting discharged from the capacitor, charge and discharge time follows this RC time constant. Okay, is this clear? This is just an approximate concept. So you have the concept of a Faraday cage. How do I make a Faraday cage? So if I have a cage, if I make it out of metal mesh, it doesn't have to be a very good conductor, but a wire mesh good enough so that currents can flow, okay, if the ground is. And then if you put a source very close, like positively charged source connected to a generator, and then connected to maybe a ground on the other side, doesn't have to be negative. Let's say it's connected to a ground, but there's a lot of positive charge like a Van der Graaf generator. I think I know how to spell it correctly, or maybe I don't. A Van der Graaf generator is a generator that can produce a very high voltage source, and that high voltage source can actually produce a very high positive charge. Maybe I can put this as a battery instead of a generator, okay? A Van der Graaf generator. And if that source is put very close to your Faraday cage, it will attract a lot of negative charge to this side of the cage, and then the charge can be supplied from the ground upward, okay? So if that happens, then you can see that this becomes an equipotential surface. And if it's an equipotential surface, then phi is a constant on this cage. And then you can also see that phi is equal to constant in this case, and the E is minus grad phi is equal to 0 inside the cage. So the electric field is 0 inside the cage. And you can see this in some museum. Here's an example of a museum in Palais de la Découverte in Paris. If you happen to go to Paris, you visit this museum, you can see this demonstration where you have a cage and somebody is trying to use a very high voltage source to hurt her, but she will never be hurt because this cage has been grounded, okay? You can also see this in the Science Museum in Boston. I'm not sure you can see this in Chicago. There's a Science and Technology Museum in Chicago. I don't think they have a Faraday cage there, but you can definitely find one in the Science Museum in Boston because I've seen the one there before, just recently, maybe 2017 I was there, I saw that. Any question on how a Faraday cage works? Okay, so that is a little bit of introduction to shielding. Okay, let's see if we can go to image theory now. I'd like to discuss image theory. Okay, image theory uses symmetry to help us solve boundary value problem. Okay, boundary value problem. And here's a very good example that if I have a charge, a positive charge placed near a conductor, the conductor does not have to be a perfect conductor, but you know what is going to happen. There'll be negative charges attracted to this conductor. And the negative charges will shear the electric field from the positive charge out there. Okay. And finally, the electric field is going to look something like this. These will be negative charges. And what this effectively is equivalent to is that the positive charge attract negative charges, and then the equivalent problem can be replaced by replacing the top problem with an equivalent problem where the equivalent problem removes the conductor. You remove the conductor, and in the bottom half space, you put a negative charge there. And by symmetry, you can see that the electric field must look something like this due to symmetry, and that the electric field does not have a tangential component at this interface. Okay, so by symmetry argument, you can put a negative charge at the bottom, and N cross E has to be 0. And I forgot to mention the fact that in this problem, N cross E has to be 0 at this surface. Okay, let me see. Even though it's not a perfect conductor, N cross E has to be 0. Does anybody know why? Why is N cross E 0 on the conductive surface, even though it is not a perfect conductor? Can anybody say something? What is the boundary condition that we have on the electric field from Maxwell's equation, irrespective of the frequency? We have a boundary condition from Faraday's law, which says that N cross E is continuous. Okay, this is from Faraday's law. Since electric field is 0 inside this conductor, N cross E must be 0 at the surface. So the electric fields are all normal to this surface due to Faraday's law, and due to the fact that the electric field is 0 inside. And for this same reason, so if you have a conductor with a positive charge there, the electric field must be perfectly normal to the surface. And that you can obtain by using symmetry argument. If I have a negative charge in the bottom half space, the electric field must add up to be something like that. And you can go through the detail that if you have a positive charge, it by itself produces an electric field like this. And if you put a negative charge there, it by itself produces an electric field that looks like that. And by the principle of linear superposition, the total field at this point is sum of this field vector plus this field vector. The tangential component cancel each other, and there's only a normal component left. Okay, that's why you have this picture over here. Any questions so far? If not, then I'll move on to the next example. Okay, what happens if you have a dipole then? Well, what happens to dipoles? Okay, so we can start with the left-hand picture. You can actually use the principle of linear superposition. You first find the image of the positive charge. By the previous argument, this positive charge will have a negative charge as its image. And then the negative charge part of a dipole will have a positive charge as its image. So if this is the electric dipole, where you have the electric field pointing in this direction, okay, this is the dipole moment pointing in that direction, then the dipole moment of the image is going to look something like this, okay? And so a horizontal electric dipole reflects to a negative horizontal electric dipole. These two dipoles are of opposite polarity. However, if you have a vertical electric dipole, this is usually called HED, horizontal electric dipole. This is the negative of the horizontal electric dipole. And on this side, if you were to align these two charges vertically, making a vertical electric dipole, okay, we call this DED. And by the same token, positive charges reflects to the negative charge down here. And this negative charge reflects to a positive charge down here by image theorem. Hence, a vertical electric dipole reflects to a vertical electric dipole also. Okay, so the polarity remains the same for a vertical dipole, but it remains different for a horizontal electric dipole. Any questions so far?
I have a question on the radiation of electric dipole. Say we
Yes.
have the electric dipole antenna atop the PEC surface. Will it be amplified, or it will be, the signal will be decreased? What will happen?
Well, what happens is that if this is a PEC, then the electric field inside will be 0. Okay. However, if this is not a PEC, the electric field will not be 0. But the good thing about PEC is that PEC is a case where the relaxation time is 0. Okay, if you look at this concept of relaxation time. If you have a perfect conductor, then tau is equal to 0, which means that if you were to change the sign of this charge, it takes no time for the charges to move around. The charges can reorient themselves instantaneously to follow the change of sign of these dipoles on the outside, which means that if I were to change this to the dynamic case, for static, then I don't need a PEC. For static, I know that a conductor is good enough. However, if this is a dynamic dipole, if it's changing with respect to frequency, then in order for me to shield it completely, I need a PEC safe surface. If I don't have a PEC surface, I only shield it partially, and there'll be some penetration of the field into the conductive medium. And if you have a perfect PEC, then this dipole is negative of this dipole. So the radiation will cancel each other. So you go to the far field, these two dipoles produce radiation field that are opposite of each other. They cancel each other. This is even more so if you put them very close to the surface. Then these two horizontal dipoles are producing fields of opposite signs, and they completely cancel each other. That's why in your homework, you're asked to prove that if you have an impressed current source put on the PEC surface, it doesn't radiate by using reciprocity argument. Image theorem can tell you that they don't radiate for very simple geometry. But in your homework, reciprocity proves it for any surface. Any PEC surface would cause this dipole not to radiate. Okay, so you can think about your homework problem number 1. And it is somewhat related to image theory, but it's more powerful than image theory. Okay, does that answer your question, Ivan?
Yes, and what will happen with the dipoles on the right-hand side, with the vertical dipoles?
Oh, okay, this is a very good question. These two dipoles are of the same polarities. Okay, so in fact, if you were to put a vertical dipole on top of a PEC surface, they add in their strength. This dipole moment becomes twice as strong. Okay, so this is a constructive effect, whereas this is a destructive effect. Okay, so the vertical electric dipole radiates better on the conductive surface. That's why you have an antenna towers. If you look at AM920, you can see that the antenna tower always looks like this, right? And then they will have a electric current flowing on this thing. And this antenna tower radiates well because it resembles a vertical electric dipole. Whereas nobody would want to make a horizontal electric dipole as an antenna tower. Okay. So you want to make the antenna tower that's vertical, especially if you are working with very low frequency, where the lambda is about 100 meters, right? Somebody told me the lambda is about 100 meters for this station. So this dipole is actually very short compared to this wavelength, so it can be considered as a short dipole. Okay, and then you can actually treat it as a short dipole and see that image theorem does work there. Okay, very good question. Let's go to the case of a magnetic monopole. If we have a magnetic monopole, then we need to have the boundary condition that on the PEC surface, n dot B equal to 0. This follows from Gauss' law. Okay, from this Gauss' law, we can show that n dot B1 equals n dot B2. Okay, and if it's a PEC, B has to be 0, E has to be 0 inside, and if B is equal to 0, E is equal to 0, then n dot B must be 0. Okay, why is it that B has to be 0 and that E has to be 0 inside the perfect electric conductor? Does anybody know the reason? Why does B have to be 0 and E has to be 0 inside a perfect electric conductor? Well, let me give you, okay, somebody has an answer.
In a perfect electrical conductor, if there is an electric field, there would be a current, and that current would go towards infinity due to the infinite conductor.
Okay. Is that Reinbart speaking?
Yes.
Okay, good. Very good. You got the right answer. Which is that, so if you have E not be 0, okay, J is equal to sigma E in a conductor, and sigma is very, very large. Okay, so no matter how small your E is, there'll be huge current flowing. Okay, there'll be huge current flowing, and the huge current will produce a very strong magnetic field. And then the BDT is equal to the curl of E will produce a very strong E field. So this would be an escalating effect if E is not 0. Escalating effect in the sense that the E field gets bigger. You just need a small E field, it produces like an avalanche effect, making the E field stronger and stronger. That's unstable. So it's not stable to have a solution for which E is not equal to 0 inside the perfect conductor. So the stable solution is for E equal to 0. And by the same token, you have the argument that B has to be 0, because if B is not 0, the slightest variation of the B field would give rise to an E field, and E field in turn give rise to a strong current, and it would be an escalating cycle of electromagnetic field generation, which is an unstable process. So both B and E have to be 0 inside a perfect conductor. And if B has to be 0 inside a perfect conductor, then its normal component at this interface must be 0. And again, you can use image theorem saying that if I have a positive magnetic monopole up here, of course, this is a fictitious because magnetic monopole does not exist, but just to help us think better, if we have a positive magnetic charge up here, and then the image of it will be a positive magnetic charge. And when both of them are linear superposed on top of each other, the total magnetic field will look something like this, and that magnetic field does not have a normal component at this interface. Okay, so now we have the knowledge, very easy for us to figure out what the images of magnetic dipoles are. Okay, so for a magnetic dipole, I will have a positive magnetic charge. It's hard to draw a magnetic charge. Let me draw it with the like cone sphere, a pine nut or something like that. Then the image of it would be the same, because the PEC reflects to the magnetic charges of the same polarity. So the image of a horizontal magnetic dipole, sometimes called HMD, will produce a horizontal magnetic dipole of the same sign. And by the same token, if you have a positive magnetic charge here, and then the image of it will be something like this, because the sign doesn't change. Okay, so this is the vertical magnetic dipole. It becomes a negative vertical magnetic dipole over a PEC surface. Okay, any questions regarding this?
What will happen if we replace PEC with perfect magnetic conductor?
Okay, if you replace this PEC with a perfect magnetic conductor, that's a very good question. Then this problem will become the dual of this problem. Okay, if you replace this with PMC, these two problems will be dual. Can you see that?
Yeah, I can see that.
Then this will flip sign, and this will also flip sign. So it will behave like dual of this. Okay, it's a very good question, but PMC is very hard to find. Okay, PMC is very difficult to find, so we don't have a PMC. But there's a very interesting effect that you can understand using image theorem, which is called the Meissner effect. That is, if you have a magnet, this is a magnet. A magnet is a permanent magnet, okay? And it can be made to be a magnetic dipole quite easily, because usually you have a north pole and a south pole in a magnet. Okay, the magnetic field looks something like this. You can buy this in a toy shop very easily. So a magnet looks like a magnetic dipole. There's no magnetic monopole, but a magnetic dipole can be bought in the toy shop quite easily. And now if you have a perfect electric conductor, which is this one, this is a PEC, and it's also a superconductor. Okay, a superconductor is something that becomes infinitely conductive. Electric current can flow with no resistance if T is less than the critical temperature. Okay, the critical temperature is actually something that is very, very small, maybe on the order of millikelvins. I don't know what the numbers are, but those temperatures have been rising in recent years. They call the field room temperature superconductivity. And that actually caused a lot of interest in scientists all over the world, because if you can make room temperature superconductors, you can have this thing turning to be a superconductor without you having to put it to a dry ice. Okay, here it's been immersed in a dry ice. Dry ice is, I believe, liquid hydrogen or something. There's a liquid nitrogen and liquid hydrogen. Liquid nitrogen is cheaper than liquid hydrogen, I think. I don't remember which is which now, but one of them is a lot easier to buy, cheaper to buy. And you can do it in your lab. You can put this superconductor, which can be a room temperature superconductor of some sort, and it becomes a superconductor. And when you put this dipole next to it, there will be an image made of this, or made from this image of the superconductor, and the image will be the opposite of itself. Okay, a north pole becomes a north pole, a south pole becomes a south pole, and so if you look at the image in the superconductor now, it is a dipole of the opposite polarity, just like what we have over here. Okay, just like what we have over here. And then these two dipoles will repel each other, causing this little magnet to levitate. This is called magnetic levitation. Okay, how many of you have seen this before?
I've seen this in the lab.
Okay, very good. Okay, if you've seen this, wonderful. If you've not seen it, you can go to the museum and look for it. I saw this in the Museum of Science in Boston. I'm sure that there are some labs around Purdue University where you can demonstrate or see this being demonstrated. Okay, so I don't know which lab we have. Maybe you can ask around in the physics department to see if you can see this Meissner effect in the laboratory. Okay, so this is really like magic, because there's nothing to hold it up except for magnetic field. forces. Any questions on this magnetic levitation?
Question: is it difficult to prove why mechanically this magnet is stable atop this superconductor?
Well, actually, that's quite difficult to prove. The thing that is staying up there is not stable. Okay, so you have to have the field in a certain configuration so that this magnetic dipole of the opposite polarity can balance that dipole on top. I don't know the detail. I presume that this is an unstable configuration. Just imagine if you take two magnets and try to balance them on top of each other. It's not easy.
Yeah, it's not easy, but as I saw in the lab, they just placed that top magnet atop the superconductor and it levitates. And this is mechanically stable levitation.
Yeah, I would imagine that it is because of the field configuration. Okay, I can imagine that if you have the experiment configured in such a way that say if you have a bottom magnet and then you have a top magnet, north, south. And if the magnetic field is such a way that the magnetic field will be something like this in the top one. And if the other one has a magnetic field that looks more like this, then this small magnet can ride on top of the big magnet's field and become stable. Okay, I'm just guessing. I never solved this problem myself before. That if you make the bottom magnet to be larger than the top magnet, you can have an equilibrium point. You can put the small magnet just right on top of the big magnet. However, if you make the bottom magnet also very, very small, then it would be hard to balance the top magnet on top of it. Okay, this is just my guess. I like you, I've seen this in the lab. I see them putting the small magnet on top of the superconductor and just balance up there. Okay. So I don't have a good answer, but I presume that it has to do with the field around the bottom magnet and the top magnet so that it can balance this. Okay. So let me go to the next point then. How do we make PMC surfaces? Okay. It's quite easy to make PEC surfaces. We just take a conductor and make the conductor as large as we want, we get a PEC surface. But how do we make PMC surface? It's not easy. PMC surfaces are surfaces for which you have, well, n cross h equal to 0, and then n dot d equal to 0. Okay, this is a PMC. For PEC, we have n cross e equal to 0, and then n dot b equal to 0. So these two surfaces are dual of each other. Okay. So how do we make a surface where n cross h equal to 0 and n dot d equal to 0? And it has to be a surface that has no surface charge, and it has to be a surface that has no tangential current. Okay, n cross h is the tangential current on the surface, and it has to be 0. And one way to make that is to use a mushroom structure. This is something done by, I think I know how to spell his name, Stephen Pico. Okay. So he made this mushroom structure very cleverly so that it consists of a short transmission line segment. You can think of this as like in a transmission line terminated in a cap, and the cap he calls the mushroom structure. And these two structures the capacitance and the inductance due to this wire can behave like an LC tank circuit. When it behaves like an LC tank circuit, then no current can flow into this structure. No current can flow at all on this surface structure. And this becomes an open circuit. When this becomes an open circuit, then N cross H is equal to 0. And then he argues that this would actually mimic a perfect magnetic conductor because it's the mushroom structure. Okay, so we don't have a perfect magnetic conducting surface in the real world, but we can make something close to it. We can only make an approximate perfect magnetic conducting surface, and you can apply image theorem to such a surface. Then electric dipoles are usually indicated by one arrow. Magnetic dipoles are usually indicated by two arrows. So if you have a magnetic dipoles on top of the PMC, it would be very similar to the vertical electric dipoles and horizontal electric dipoles on top of a PEC surface. You can see that this is just a dual of the electric dipoles on top of PEC surface. You can also see that this is just a dual of the magnetic dipole on top of the PEC surface. Okay, so you can go to that quite easily, and it's not too difficult using duality principle. So let me just write down that you can understand this using duality. PLE, using duality principle. Any questions on this? If not, let's go on to other more sophisticated image theorem. So we have just used a flat surface to invoke our image theory. It turns out that image theory can also be invoked for sectors. Like here is a 90-degree sector. Okay. And you can solve this problem piecemeal. First, you assume that this part is not there and try to solve this problem by assuming that this is infinite in extent. Okay, you assume that it's infinite in extent, assume that this is not there. Okay, then you put a positive charge here. You should have a negative charge as an image, and then you put the negative charge there. You will have a positive charge at the image. But by the placement of this positive and negative charge, you know that the tangential component of the electric field is 0 on this line, okay, just by symmetry. Just by symmetry, the tangential component of the electric field must be 0. So N cross E must be 0 on that line. And hence you can add in the PEC surface, okay, on that line without disturbing the boundary condition. And hence this configuration of 4 charges solves the boundary value problem of a 90-degree sector. And you can repeat the same if you have here a 60-degree sector. What do? You again assume that this thing is of infinitely long sector, and then solve this problem by having a positive charge there, a positive charge there, and then negative charge here, positive charge there, and then you can add in a PEC surface, and then you can further add in image of this and image of that, and the image of that you can add in the other PEC surface without disturbing the boundary condition. You can show that on these surfaces, N cross E is equal to 0 quite easily by symmetry argument. Okay. Any questions regarding this image theory for sectors? It's all by symmetry, and also you can do, if you have 2 parallel mirrors, and you probably have sit in front of a mirror with one parallel to itself behind you, you see infinite images of yourself in the parallel mirror. Okay, the same thing happens here. If you have a positive charge, the image of itself is a negative charge, but if you put another PEC surface here, okay, this surface is going to reflect these two charges in this manner, and they keep reflecting each other infinitely distance away, so that you have a series of infinite images in order to solve this boundary value problem. Okay, this you have seen at home, or maybe in some of your homes you have this parallel configuration of mirrors. You will see that in your home. But what is more interesting is that if you have a sphere or a cylinder, you can show that this thing is not very symmetrically placed. This thing should be slightly lower down. Okay, it's not very symmetrically placed. It's on, should be on this line of symmetry. So you put a positive charge here, there should be a negative charge on this cylinder or sphere surface, and I should call this Q image. Okay, and then you can show by arguments that if you adjust Qi judiciously and put its location also judiciously, you can get the electric field to have no tangential component on this sphere surface. Okay, the argument is given in Ramos' book. I don't hold you responsible for this, but you should be aware that the solution is there. So next time, if you need to find the solution to this problem, you can know that you can find it in Ramos' book. Okay. Similarly, if you have a charge, Q, positive charge, placed on top of a dielectric interface, there is an image charge. The image charge is given by this formula. This formula can be derived using Fourier transform. Okay, I'm not going to show you the derivation because the derivation is kind of complicated. But once you know how to do that, you can show that such an image exists. I'm not holding you responsible for this image theory, but I just want you to know that this image theory exists. And you know where to look it up. You can look it up in my textbook if you want. Okay. So let me go on. Any questions regarding image theory? If not, I'd like to talk about high frequency solutions, Gaussian beams, and how you solve problems when the frequency is very high. Okay.
I had a question real quick.
Yes, sure.
For the sections specifically, can we expand that into spherical or cylindrical geometries as well, and not just rectangular or Euclidean?
Oh, you mean this one, the sectors?
Yeah.
Okay. I think we actually are not solving this problem using any coordinate systems at all. We actually just invoke symmetry arguments. So it's coordinate independent in that sense. I don't care. I don't think even about coordinate systems. You see what I mean?
Yeah.
It's all physical arguments. So I'm all using physical arguments which are coordinate independent. I say that if I put an image, if I put a charge here, it should have an image there. And then if I put another one here, it should have an image there. But if you look at the foursome together, there should be no tangential electric field on this plane. So I can put a PEC surface there. And similarly, I can say that if I have this foursome, okay, then it produces zero field on this plane, and hence I can change this to half, okay? And then if I couple this with its images and couple this with its images, and then this, all 8 sources together produces tangential electric field at 0 on this surface, and hence I can insert this PEC surface without violating the boundary condition. So it's all by symmetry argument. There's no need to think about what coordinate system I'm in.
What would the images look like if the sector, instead of being a triangle, was something like a parabola?
Oh, that would be very difficult. That has no simple closed form solution. If it's a parabola, I'm not sure if a closed form solution exists. I know that if it's a sphere, a closed form solution exists. And what happens is that some of these solutions are really weird. Okay, I've read about them. So if you have this one, you might have this very simple solutions. And if you have something that is less ideal than a circle, so you're asking me if I have a parabola, if I put a positive charge here, what is the image? Sometimes the image gets smeared out, okay, smeared out. You have negative charge cloud. And that happens. I'm not absolutely sure. The problem becomes increasingly difficult as the geometry becomes less and less simple. Okay, you're asking me what happened if this is a parabola. Okay, if it's very simple, it would have been taught in this course. If it's not simple, it would be found in some dusty old textbook somewhere, or maybe in some library book somewhere. Is that a fair enough answer?
Yes, thank you.
So nowadays, the wonder of the modern world is that a lot of these problems can be solved using computers by numerical methods. So closed form solutions are they're useful, of course. We cannot downplay the importance of closed form solutions because they offer us physical insight, but numerical methods, which you're going to touch on, okay, they allow us to solve all manners of complicated problems in the future, okay? So let me move on to talk about high frequency approximations. How do we solve problems when the frequency is very high? Well, there's something that we can do, which is to make the tangent plane approximation. We know that if you have a spherical wave, if we have a source, okay, we have a source, and we know that if you go far away from the source, the wave becomes a spherical wave. Okay. And if you are far out enough so that the wavelength compared to the radius of curvature, okay, lambda is much, much smaller than r, then this becomes a local plane wave. Okay, a spherical wave becomes a local plane wave if you're far enough from the source. Okay, and what is more wonderful is that a local plane wave, when it impinges on the surface, you can make what is called a tangent plane approximation, assuming that this wave is coming in, and the wavelength is so short compared to the radius of curvature here. Okay, this radius of curvature is much, much larger than lambda. Then you can also argue that this surface is locally plane. And because this surface is locally plane, the way it reflects an incident wave or incident ray, you can think of this now as an incident ray. Okay. You can think of a ray as being part of a spherical wave, where if you go far enough from the source point, the spherical wave becomes like a local plane wave. Okay, that is what you can think of as a ray. Okay, so you can think of this as being equivalent to a ray. And if you have an incident ray, you can think of that ray as part of a spherical wave due to a source that is very, very far away. And by the time that ray reaches the surface, it becomes locally a plane wave. But you can only think of it as a local plane wave if you confine yourself to observation points that is small compared to small compared to the radius of curvature, and then a region where the wavelength is small compared to the radius of curvature. And then you can think of phase matching requirement. If this wave is going to bounce off this surface, because it's locally plane, the kind of physics that happens here is going to be plane wave physics. And plane wave physics similar to the case of a Fresnel reflection coefficient. Fresnel reflection coefficient operates by phase matching. Okay, Fresnel reflection works because of phase matching. Okay, some physicists also call this momentum matching. Momentum matching is the same as phase matching. So you have phase matching condition here, the reflected plane wave, or local plane wave, and a transmitted local plane wave, and the incident local plane wave has a phase match at that interface. Because they have the phase match, they follow a local Snell's law. Okay, local Snell's law. Does that make sense to you? Or do you have any question on this approximation? So because of this tangent plane approximation, local plane wave approximation, and the fact that you can replace things with tangent plane physics when the wavelength is very short compared to the radius of curvature, then you have the field called ray optics. Okay, so if you want to study, say, the reflection of electromagnetic wave by a lens, you assume rays coming in, and then they will pretty much follow the local Snell's law. Okay, they will follow the local Snell's law at these surfaces, and then the light will refract and reflect according to the local Snell's law. And using this understanding of the physics, you can actually understand how rays should be reflected and refracted and do geometrical optics or ray optics. So there's no solving of PDEs. You just have to trace ray. And if you know how to trace rays and trace how they should propagate through this complicated medium, you can actually use or extract interesting physics from this, okay? Like if you know the refractive index of the material, which is usually given by epsilon over epsilon naught, this is the refractive index. Okay, you can do this kind of GO approximation on solving the problem. Lens design, okay, lens design, I hope I spelled it right. Lens design is such a thing, and also the movie industry. Now, a lot of the movies that you see coming out of Hollywood actually does a lot of ray tracing. What they do is that you have a room, and you shoot rays inside this room, and then you follow and track how the rays will bounce off different objects in the room. And so if you watch the rays coming out of the room, you see very nice effects coming out of the room using ray tracing algorithm. So the movie industry is actually inbuilt and obsessed with this technology. And if you are a very good ray tracer, if you know how to trace rays, you can find a job with the movie industry. Okay, another one is, of course, computer animation is another place where they have a very active interest. Okay, any questions regarding this? A large part of the technology in optics has been done by this. We make our glasses, we make all kinds of astronomy lenses and so on using gray optics. Okay, any questions?
I have a question on terminology. What is the difference between geometric optics and physical optics?
Oh, okay, that's a very deep question. Okay, that is a very deep question because what geometrical optics just assumes ray tracing. Everything has been treated like a ray. Okay, physical optics is something else. Physical optics says that if I have a scatterer, I can find the problem using geometrical optics where I just make tangent plane approximations. And in physical optics, you actually find the surface current. Okay, the current Js is n cross h. Okay, you try to estimate this current. And instead of tracing the ray, you assume that you have these currents flowing on this surface. These are called impressed current. And from this current, you can calculate using Green's function method. Okay, you probably have learned by now that once I have the current, I can compute using the diadetic Green's function. I assigned this as part of the last homework. Okay, I hope it wouldn't blow you away. Okay, so once you have the current, and if you know what the diadetic Green's function of the system is, conceptually it's very simple, but then it's a bear if you have to do the mathematics behind it. Okay, and then you calculate the field. That is called physical optics. So in other words, you estimate the currents first before you calculate, rather than you do ray tracing. So it is, in a sense, a step better than geometrical optics. Okay, but these are very advanced topics. We wouldn't talk about it at all in the course. Let me tell you more if you are interested. So the next thing I like to talk about is actually Fermat's principle. Okay, Fermat's principle. Actually, it's amazing because it was actually done in the 1600s. It is a statement of ray optics. Okay. Actually, I was told that in the year 984, Islamic world was actually quite advanced in science. They actually know about this kind of thing in the Islamic world. So what it says is that if I have a very complicated object, and then if I were to shoot rays, and the ray can propagate by different paths due to refraction and so on. And if you have a ray that starts from a source point here, A, reaching the observation point B, the ray that will be followed by the electromagnetic wave will take the path of minimum phase delay. So the light ray always follows the path of minimal time to go from A to B, if you calculate the travel time that the ray needs to travel. And in terms of frequency domain, this is also the same as minimal phase delay. Okay, minimal phase delay. Okay, so that is just Fermat's principle. Any questions on those?
Is term optical path related to the same question?
Yeah, it's the same optical path, okay, or ray path. Sometimes we call it the ray path. Okay. So if you don't have question, I will apply a very simple application of this Fermat's principle. Okay, let's see. So let's use Fermat's principle to derive what we call a generalized Snell's law. Okay, generalized Snell's law. Let's assume that, actually I have a picture here, so I might as well use that picture. Okay. Let's assume that we have this picture and that we have a source here. We give out a ray, and then the ray would impinge on this surface and get refracted. I like to show that you can derive Snell's law by using Fermat's principle. Okay, so what you need to show then is that the phase delay or time delay, they are the same thing. One is in the time domain, the other one is in the frequency domain. The phase is equal to Ki dot Ri plus Kt dot It. Okay. And then you can show that Ki is using the picture on the left. Let me see if we can make it bigger. Okay, it doesn't become bigger. So I can use this picture. If I write down Ki dot Ri, it would be the phase going from A to B. Okay, and then Kt dot Rt is the phase going from B to C. And this phase should be minimized. Okay, this phase should be minimized. I would minimize it by moving the point B. You can move it around until this phase delay is minimized. So how do I set up the equation? I know that this phase, the total phase delay, is given by this product, this dot product plus this dot product. And I'd like to minimize this phase delay by changing it with respect to xi. Okay, I would change xi until this phase is minimum, but I know that for this problem, as you can see, xi plus xt is equal to a constant. Okay, it's a constant because xi is this part of the length, xt is this part of the length. They don't change. The total of them does not change. Okay, so if I were to write out p, okay, can also be written as kix xi plus kit xt plus the rest. The rest does not depend on xi and xt. It depends on functions of y. Okay, so if I were to differentiate with respect to xi, I will get kxi and then kit dxt dxi. But the xt, the xi is equal to -1, okay, from this relationship. So this has to be 0 according to Fermat's principle. So this says that kix minus kit sorry, this should be Tx here. This is X component here, X component here. Okay, I have to take the X component of this. Well, this is not Ki, this is KTX, sorry, Tx. Is equal to 0, okay? So this is the same as Neal's law. Kix is Ki sine theta I. The X component of this is just Ki sine theta I, okay? And then KTX is KT sine theta T is equal to 0. Or Ki sine theta I is equal to KT sine theta T, Neal's law. Okay, Neal's law. So of course, Neal's actually derived this using phase matching, not by applying Fermat's principle. Okay. So any question on this Neal's law using Fermat's principle? If not, then we can move on to doing something rather interesting. So if we are able to design a surface called a meta-surface, that the surface is made of nanostructures. These structures are much smaller than the wavelength. Okay, so instead of making the problem translationally invariant, I will have to add a phase function that that the phase now, depending on how which part of the surface the ray goes through, that the phase is Ki dot Ri plus Kt dot Rt times the phase function. Okay, let's assume that this is the model now. Depending on which part of the surface the ray penetrates, the ray will see a different phase function because I make the surface such a way. This is from Capasso's group. Okay, this is from Capasso's group in Harvard. Federico Capasso, Harvard. Okay. So he adds this phase function to this meta surface. Then if you were to now find the optimal solution for the Fermat's principle, which means that if you were to change xi, you will get the minimum solution to be 0 according to Fermat's principle. You get Kix, and then you will get KTX from here. And then you will have an extra term now. Okay, because of this phase function. So you have an additional degree of freedom. You have this additional degree of freedom, and this is called generalized Neal's law. Neal's law does not have this term, but Capasso brought that in, okay? And of course, at Purdue, if you want to talk about this kind of structure, you can talk to Professor Vladimir Shalat. His lab makes this kind of structures, okay? And what happens is that nanofabrication has become so advanced that these structures can be made much smaller than the wavelengths. If you look at blue light, the wavelength is about 500 nanometers. So you can make these structures on the order of tens of nanometers and make surfaces that have this extra phase function that describes it. And then the light ray would refract differently depending on which part of the surface it hits. And then you can make very fancy lenses. Okay, you have a lens. You can have a okay, the light ray would refract. Okay, you can make fancy lens. Okay. Also, one of the things that have spurred the development of this field is that this phase function is not easy to estimate. So, but you can use computational electromagnetics. Which is the numerical method of solving this problem. And you can use computational electromagnetic to estimate this surface and find the proper phase function to fit it. And then you can do all kinds of wonderful things with it. Okay. Are there any questions? I think I'll stop here. And next time I'd like to talk about Gaussian beams. I'll talk about Gaussian beams in the next lecture. Okay, but
just a quick,
yeah, sure.
Just a quick question for our professor. Typically, what are these metasurfaces? Like, what materials are these metasurfaces made out of?
Oh, okay, that's a good question. These metasurfaces are made of a number of materials. Usually, they are called surface plasmonic materials, like gold or silver. Gold or silver. This is gold. Silver. I guess you know that there are something called surface plasmons inside this metallic structure because a metal like gold or silver behave like a plasma. You understand that, right? So if you have a sea of electrons, and if that sea of electron behaves like plasma, then the epsilon can change rapidly as a function of frequency. And some of these structures can even resonate, have surface plasmon resonance. Hence, the permittivity can be engineered to change very rapidly. And I heard that you can make these materials out of gold and silver. You can talk to Professor Vladimir Shalev, since he makes these materials in his lab. I think a few of Professor Shalev's students is also in the class. So you can ask them as well. Okay, is this fair?
Yes, thank you, Professor.
Yeah, anybody wants to give a feedback as to what materials you usually use to make these metal surfaces? Anybody from Professor Shalev's group? Nobody? Okay, nobody wants to say anything, so let's just let it be then. Any questions? If not, I'll let you go, and then we continue with the Gaussian beam next time, which is also a very interesting topic. High frequency topic. Okay, this is Fermat's principle, generalized Snell's law, and so on. Tonight there'll be an office hour given by Dr. Na. Okay, at 8 p.m. so that more people can participate. Okay, see you tonight if you are going to Dr. Na's office hour. And have fun with the homework. Okay, bye-bye.
Thank you, Professor Chu. Bye.
Okay, bye-bye.